Hi, I've been taking another look at non-volatile storage options for the Raspberry Pi Pico. The Pico comes with its own flash on board, and we can use it for more than just the purposes of storing code. It isn't trivial though, and in this video I walk through some of the steps and considerations. I look at options and examples to store your persistence variables into that flash memory. Working with Flash using the base level functions on the API requires quite a lot of design work. What we miss on the Pico is a great library like MVS library available for the ESP32 microcontroller. So I've produced a library inspired by MVS library. It handles single core, multi-core and the FreeRTOS kernel in a single core situation. More on that later in the video. Please do like the video and subscribe. I really do appreciate it. Flash is different from normal memory in the sense that it's non-volatile storage, i.e. when we turn the power off, that data is still held there and stored. So when we turn the power back on, we can actually read it from our program. It is limited in the number of writes. Unlike main memory, you can only actually write to flash storage a few 100,000 times or so. Certainly, if you try to write to it every tenths of a second as you would normal memory, you would actually break it and kill flash quite quickly. It's fine for non-volatile usage, but we have to treat it just like those SD cards that you write to. They work great for a while, but you can kill them by overwriting. Certainly, all those Raspberry Pis you've eventually killed because you're running your file system off an SD card. The write process is actually also a little bit different from Flash. You can't just write to a byte in Flash. You actually have to go through a process which is to first erase and then write. And the bit you are erasing is actually a large segment of the flash, and then you write to a page of that segment. We'll talk about that a little bit more because those are quite key concepts. So how would I want to use Flash? Well, we use Flash all the time, to be honest, on the Pico because it's where our code is stored. So every time we put our code onto the Pico, well, we flash it strangely, and we write it to the flash memory. I also want to use it though for things like storing local configurations, so Wi-Fi access point names and passwords, perhaps SSL certificates. Perhaps in some IoT projects that have dodgy connections to the internet, I might also want to look at actually sampling data and storing my sensor data within Flash, and then when my internet connection comes back up online, then actually sending it all in one go. And you can also do things like emanate a file system, and Python does that with some of its stuff when we're using a Python emulator on the Pico. But we might want to emulate a file system in order to provide web services or send out images or manage images on the Pico. Now the Pico and Pico W have 260 kilobytes of RAM, but 2 megabytes of flash. So there's a lot more flash available to us than there is RAM. And strangely, it actually runs the code from the flash to save that RAM for our variables generally. There is a little bit of caching that goes on the code to speed it up actually, but generally the concept is code runs from flash, we store data in RAM. Now, other boards out there, non-Raspberry Pi boards using the RP2040 processor, actually have even more flash. The Tiny 2040 comes in a version that's got 8 mega flash. The RP2040 stamp has 8 mega flash. And the Adafruit's Metro RP2040 comes with a massive 16 mega flash. So actually, flash for storing these things is actually readily available, and we can find some quite bigger boards out there to use for this. They do this because the flash is actually not on the RP2040 core, the actual processor that the Raspberry Pico uses. It's actually a separate chip and communicates via SPI. So how do we look at the flash? Where does it sit? How does it occupy our Pico? Well, it's actually just mapped into memory. So the flash is just a block of memory that sits above RAM. It's actually address hex 1000 in memory, but you generally access that using the definition XIP base. That gives you the base position of where flash starts. There's also the Pico flash size in bytes definition available for us in C and C++ to tell us how big the flash is. So we know that it's 2 meg on the Pico and Pico W, but some of those other boards, they will give us the definition to give a much bigger flash size. Provided, of course, you set the board correctly in your make files. Now, our code is going to be written into the flash, and our code starts from the bottom of the flash up. So if we want to use the code for some non-volatile storage purposes of our own, it's best to use the top down. And that's what I'm going to do. Now, when I'm addressing flash for write, it's actually rather different. I'm not addressing it as part of memory and it's mapped into the memory at all. In fact, I just treat it as a block of flash starting from a 0 position up to the size of the flash. Now, this can be confusing, and you need to think about this when you're reading and writing from flash, that actually the addresses you're using are different for read and write. So now when we write, we go through a strange process. We first of all need to erase a segment of the flash. We can't just write to it. We first have to erase it and put it into the right state so that we can write to it. And you erase a segment. And the segments are 4 kilobytes in size, so 496 bytes. So you can have multiples of that if you wish, though actually a 4K is quite a good chunk, I would say. But minimum is 4K, and yes, has to be exact multiples of 4K. Similarly, when we write in what are called pages, and a page is 256 bytes. Again, we must write it in pages. We can't just write a single byte, and it must be exactly multiples of 256, or the core will just panic and nothing will happen. This video is sponsored by Cancun. Cancun is a friendly retailer in the UK for modules, components and electrical equipment. Cancun has kindly offered a discount to my channel viewers on the first order. Just quote Dr. John EA 20 at checkout to get a 20% discount. This excludes electrical test equipment and tools. If you're in the UK, go and check out Cancun today. All the code for these experiments is included, of course, on GitHub, and you're free to go and get a copy of that. So the first example I'm going to show is just how to do the basic erasing the flash and writing a page to that flash. So we're going to erase 496 bytes, which is the size of a segment and the minimum we can actually erase. And then we're going to write a single page, and that's going to be 256 bytes. Again, the minimum page size that we can write using the API. And then we read back that string and print it out. Pretty simple. Let's have a look over in the code in VS Code. So we're in this first bare metal, and this is a really very simple program. The first thing I'm going to do is use a few definitions to set up. So what is our page size? It's 256 bytes. That's what we're going to write. What is the size of the segment? That's this MVS size, and it's 496. Again, that's the bit we're going to erase. Those are fixed with the API. So we can say then that when we write, we're going to start writing from that MVS size from the size of the total size of the flash. So we're using that top section of the flash to write to. when I'm going to read, obviously I've got to actually take the offset of XIP base first from that, so we just add that on. So that gives me my reading and writing locations to get to that top section of flash. So we create a string that we're going to write here, and I've made that the whole of the page size, even though I'm not using any of that, so that we've got a nice safe bit of actual memory that we're going to copy from to write into the flash. And then to read it back, I'm going to create a flash string variable, and I'm going to make that point to our read location within flash. So that's the bottom of our flash segment that we're using. As always, I'm going to initialize standard I/O. I generally give it 2 seconds just to stabilize, and then print out we're starting. And then we're going to use the flash range erase code to actually erase that area of flash. So where we're starting it, and that's again the address within flash, not the address in memory. And the size of that, which is 4096. And then we're going to write to it, and then again we're writing to the flash write location within flash, not in memory, and then we're going to give it the address of our string and the page size that we want to write. So that's it. Well, at that point flash should be written, and we can just print it back, so we can look at what's in this flash string variable, and that is pointing to a location in flash, so that will be pulling that data from flash to print out on the screen. So let's see that as a demo. So our first example really isn't very safe, because we are not actually protecting those arrays and write functions from anything else going on the core. So we could have interrupts running, and when the interrupt triggers, it's going to suspend what's going on in the arrays functions, and it's then going to actually probably try and read from the flash, which is going to break everything. So it's really important that we build a critical section around this code. And so in this example, I'm going to do that and show one approach to achieving that. So over in VS Code, we have the 2 bare metal interrupt example. And if I open up this example, again, it's very simple and it's pretty much the same as we've done before. But this time I'm going to write a new function in here, which is going to be a timer callback. So I'm going to run a repeating timer, and that timer is going to just keep going in here and doing a bit of maths, enough to really interrupt my write to flash process. So you will see here I'm going to, after we've starting, I'm going to add in this repeating timer. So I've got to do something where I actually disable the interrupts. So I disable that timer while I do the writing to the flash, and then I can re-enable it. And there's an easy couple of commands in the API to do that, and it's save and disable interrupts. We'll save them and disable them. I've got their status, so then at the end of my critical section I can re-enable them. Erase and write is just the same as we've done previously, and then we can print out the value that we've written. So the demo will look exactly the same as you've already seen, so I won't show you that again. What we've looked at so far is all about a single core and what's running on that single core. But a Pico, of course, has 2 cores, so we can have stuff also running in parallel on the second core. Now this is a problem for us, because not only might that be accessing data that's stored in the flash, it certainly will be running code, and the code's stored in the flash as well. So we can't actually flash or write anything to flash while the second core is running. We've got to suspend it. So we need to actually add into our code the ability to halt the second core temporarily while this flash stuff is running in this critical section, and then re-enable it. Let's have a look at an example that will do that. So over in VS Code, we've got my bare metal 2-core example. And this time I'm still going to be running our wonderful little interrupt, but I'm now actually going to run a new function for the second core to run. And this function is going to go and do some maths, some square roots, and it's also going to flash the LED just to make sure that I can see that things are actually running and that I have re-enabled this function and it is still running. The most important thing that this function is going to do is at the beginning, when it is going to declare that it can be a victim of lockouts. So it is allowing the other core to lock it out. And that's exactly the mechanism we're going to do. So our main code is exactly the same as before, with the exception that we're going to now start that new function on our second core. And then we are going to additionally, within our critical section, lock out the second core from operating and then re-enable it. So that's what's going to happen, and then it's going to then print out the value that we've stored to flash. Again, the output on the screen is going to look identical to what we've just done in the two other examples. So I won't show you that. So we're doing a lot more in this example because we're going to shut down all of the interrupts and we're going to shut down any work going on in the second core so that we can safely write to the flash. To be honest, there's a lot to think about when you're writing to flash, and doing that using these base level SDK APIs all the time is actually a pain. I program on some other platforms as well as the Pico, one of which is the ESP32 and the ExpressIF platform for that microcontroller. Now that's got a really lovely library called Non Volatile Storage, which actually handles all of this stuff of writing to flash for you and makes life a lot easier. So I thought I'd have a go at trying to rewrite some concepts from that library into a library that I can keep reusing on the Pico. So that library is published on my GitHub page as RPI Pico onboard NVS, non-volatile storage. And really what I'm doing there is just taking ownership of part of the flash and creating an NVS area within that flash, which is by default, of course, 4K in size. Actually, it could grow and you could have a large one, though generally I think 4K is probably the size that nearly everyone will run and use, because I can't see where you get much bigger than that for this concept. And what I'm actually storing in there is key value pairs, so that makes it easy for any of my code. There's no worrying about order, there's no worry about libraries. Everything just sets a key for the value that they want to store within there and retrieve from that MVS area. I was thinking when I was writing this that, well, those keys are going to take up a lot of space because they're all strings, by default up to 16 characters length. But to be honest, we've got 4K. We've got loads of space. Considering what I'm really going to store there, which is probably going to be Wi-Fi access keys or at most SSL certificates. So it's actually not going to be very full. So to operate on the MVS, then we are able to get a value by its key. We're able to set a value giving a key and a value. And then when we want to actually write it to flash, we issue the command commit. We've also got rollback there. So if for some reason I just didn't want all the stuff I just set, I can roll it back without committing and I go back to the state of whatever was stored in flash. Let me show you a little bit of the code here, because I've set this up as a project. It's available for you to download from GitHub. And really it is only two files here. It's just our NVS onboard object. And NVS onboard object is a singleton, so we can access it via when he gets to finds the right bit of code, we can access it with the get instance command. Actually, you can also destroy the instance, mainly because I needed to do that for test purposes to validate that actually everything was memory safe. And then we have basically get and set methods for every data type that I'm supporting. So integers, 8-bit, unsigned and signed, 16-bit, 32-bit and 64-bit, some strings and some blobs, so store whatever you like in there. And we then, of course, got the commits. Here we go. We've got commit, rollback. We can also clear, which is a little bit different from rollback, so actually just nuke it and take the whole MVS back to a completely clean state with no data in it. Check to see if a key's been used in there and have a look at what the number of keys are. Check if it's dirty, if it needs to be committed. And a bit of debug, we can actually print out the status of all of the keys that are included within the MVS. So that's what I've written. And there is a test program here. There are also lots of CPPU tests that I've written using this to show all of the different combinations of all the things that could interfere with this and that they work. So the test program, though, all it's doing really is creating a reference to our MVS onboard instance, checking to see if a new key is in there called demo. If it is, then it's getting the value of that. If it's not there, it just says it's not there. And then we set the value of that key +1 back into the flash. That's it. And let me just show you that running as a demo. And you can see here, as I keep pressing reset on the processor, we're actually just slowly incrementing my demo counter. I've talked through the code and challenges of the flash in quite some detail. I hope that was useful. Please do let me know in the comments. I'd also love to hear if you find my library useful. I've skipped explaining how the flash can safely be used when you're using FreeRTOS kernel. That's mainly because I feel I haven't fully solved that problem, and that mainly the issue is there with this symmetric multiprocessor variant. Let me know if a video on FreeRTOS kernel and flash memory would be helpful. Thank you very much for watching. Please like the video as it helps others find it, and please subscribe and hit that notification button so you don't miss the next video. Bye bye for now.